I want us to be familiar with bits of notation, and I'm hoping that most of this would be familiar already. When you see R with the two lines on the R, the backbone of the R, we know what this is, right? So it's going to be the set of all real numbers. And then R squared is going to be the pairs of real numbers. So more mathematically, this could be described as the set of x, comma, y in parentheses as ordered pairs. And then we have a vertical bar in math when we're talking about set notation. This says this vertical bar is like such that. It's that phrase, such that. X and y are elements. Now this little e here is to say an element of a real number. X and y are real numbers. Yeah, so let's say it in words. The ordered pair x, y such that x and y are real numbers. And this symbol in words, if you were to read this, you would say is an element of. Okay? Some more notation. We are very familiar with y equals f of x. F of x is a representation of some arbitrary function. And so in this statement, you can identify what the independent variable is and the dependent variable. And the independent variable would be the input. And then your output is the dependent variable, which gives you a value. So you've probably seen that notation, but this notation, you might have seen it, but probably is less used or less familiar. A function that takes a real number as an input and then gives you another real number as an output. F takes a real number input and outputs a real number. And then sometimes people tend to combine these two notations together. And if you're looking at individual values themselves, like the x and the y, the input and the output, you tend to change your arrow a little bit to have this little vertical, mini vertical bar. Say that this function f takes x as an input and then outputs y. Okay? And then in terms of these types of functions, you guys extensively studied in pre-calculus. You guys studied the domains and ranges of things. So you might be familiar with those. Maybe not so extensively. You guys might have taken a look at what it is to be one-to-one and onto. I think that's kind of important. It's more important if you're going to be a math major or maybe a science major. I don't know. But I think this is some of the basic notation that you need to be able to understand so that when you see or read things in the textbook or when you see or read things of the notes that I put up, you would know what they mean. So I only went to R2, but of course there's R3, R4, R5, etc., right? We can go as long as we want. And we don't, in general, in math and other disciplines, you're not just restricted to real numbers. I know in physics, complex numbers come up a lot. So there's another symbol for that set of numbers, complex numbers. And then there are other, I don't know if Professor Tong does this in his linear algebra class, but when I teach linear algebra, I talk about groups of integers, circular groups of integers. And so they are called a special number notation.
Sorry, what is the line on, or what is the scale of the arrows?
That just means I'm not looking at sets like I am here. Here I'm looking from one set to another set. Here I'm looking at elements from one element to another element. And that's what this means. It just takes an element, and then it gives you an element x, and then it outputs an element y. All right. So today, most of today, our main focus is going to be this. Now, based on what I've just been talking about, can you describe what this is? Let's see if you can put it in words, Joe. Okay, that's a good description. Matt, were you going to say something different?
I was going to say something similar to that.
Okay. So it takes.
So f is a function of two variables. We input two variables.
Yes. So you input two variables. F is a function of two variables. You input two numbers, two real numbers, and then your output is whatever your output is. Okay? This is actually a nice teaching spot for computer science. And when you talk about functions, and here is an example of a function that might take in two variables. Oh, let's do some computer science. Anybody know how to program? So let's do pseudocode. What's pseudocode? What? Yeah.
Just like an outline.
Like an outline. Yeah. Yeah. So I'm not going to adhere to a specific language, computer language, but let's just say this is a silly, this is kind of a silly example, but let's take, for example, our function f. So we're going to define function f. Function f. And then let's say the f takes in two real numbers. I was going to put double. What's that? C or C++? Yeah. 32-bit. Something like that. I don't know. I'm just spewing off some computer science stuff. Let's say it takes a real number x and then the real number y. And then let's begin our function here. I'll put open parentheses. And then let's just add them. That's kind of a boring function. Actually, I probably need another variable. Oh, we don't need a temporary variable. Let's just return. Sorry. Return x plus y, and then close. So this is a simple function. It takes in an x value and the y value. It takes in two values, and then you're just going to simply add them. So this is an example of a simple pseudocode for computer science. If you're going to do C or Java, you would or Python, you would translate this appropriately, and then you would have a running function by calling it. Okay? So for us in math, we have more flexibility because we don't have to follow syntax or anything like that, but we do it. There is some sort of syntax and parsing that's going to be important for us. So we would say f as a function of two variables, and then we would define more or less what it does. So we can write it like this, and then now we have a function of two variables, x and y. So our function of two variables can be written as f parentheses, and then the two variables that you're talking about, a is equal to x plus y, or whatever, plus whatever. All right. Is there another function that might pop up in your heads when we think of functions that take two numbers for an input? Yeah? That's just another generic one. So let's say another example. So it sounds like we can do whatever we want with the x's and y's and then create whatever function we want to create, just like we've done back in pre-calculus, right? So we can include sines and cosines and then do stuff with it. So these are examples of some simple functions. I was thinking more of like a real life function. Finding the area? So now, as in algebra or calculus, the f is just the generic name. The x and the y are just generic names. So what's to say we change the variables to whatever we want? So instead of f, what if I call this a? And instead of x, what if I call this L? And what if instead of y, I call it W? Then we have something that kind of is familiar to us. And let's say our function now is L times W. Now we just came up with the area function. All right? So you can include units here if you want, or you can just not and say whatever that is what it is. But that's, we deal with functions of several variables, I think a lot more than just regular single variables. There's another one that I think it's interesting that I wanted to show you. I didn't prepare this too much far in advance, and it doesn't affect us because we're in California. But if you've ever visited or lived in like the East Coast where it gets really, really super cold and the wind picks up and then it feels even colder, they have what's called the wind chill factor. So if you think about the wind chill factor is actually a function of two variables. It's the temperature, right? How cold it is. That certainly plays a part in the wind chill factor. What else? The wind, the speed. Well, we can mess with the humidity, or let's not. But if we just keep this with just the temperature and the velocity of the wind, now we can describe this as a function of two variables. What? That's not.
Click on the IMDb page for the film Windchill from 2007.
Wow. Now, where was it? How is the wind chill calculated? Now, if you look at the wind chill factor, if people look at the wind chill factor, and just imagine like a weatherman, weatherwoman, non-math person, and then they would deliver this in the news, or they would look at this. This is our official formula, or it changes once in a while. That the wind chill factor is dependent on two formulas, or two variables. Now, can you see the variables here? Right? So I can write this as W or WC for wind chill. So let's write it a little bit more mathematical with our notation. We can say W of what two variables are we using here? T for the temperature and V for the velocity of the wind. I'm not going to copy everything else down, but it's basically this whole thing now. So you got the velocity raised to the 0.16 power. I don't know who the hell came up with that, but that's the wind chill factor. And anyways, when people try to find the wind chill factor, they tend to not use a formula like this. Do you know what they use? You guys been to the East Coast? No? Yeah, they use a table. So they use a table. Now, when we used to graph back when we were kids, graphing the functions from R to R, just y is equal to f of x, we would have two columns and stuff like that. When you graph, or not graph, but when you find numerical values for these functions of several variables, the graph or the numerical table gets a little bit more complicated. And so if we take a look at, see, this is my search. Where's my search? If we take a look at the wind chill factor, and let's see, I'm just going to click on images, you see something a little bit different. Ridiculous history. Most of the time when people try to figure out what the wind chill factor is, they just rely on the table instead of having to use a complicated looking formula. And as scientists, I'm hoping that you would be able to take a look at this table and understand how to use it. But let's take a look at how to use this table. Is this the same formula? 35.75, 0.42, yep. It looks the same. So what you have is a column of values that would describe the temperature and a row of values, in this case, that would describe the wind speed. So this is your T. I'll use red here. And this must be your V values. So if I were to ask you, based on looking at this table, what is the wind chill of, let's go 10 degrees and the velocity of 35 miles per hour. So this is saying degrees Fahrenheit, and then wind speed of 35 miles per hour. What would you tell me the wind chill factor is? -14. So I would go to a temperature of 10 and the wind chill, or the wind speed of 35. Then I get my value out from there. So although it's 10 degrees outside, the wind is blowing really hard. If you go outside, it actually will feel like -14 degrees. I was in North Dakota once when it was like -17 with the wind chill factor. Whew. Cold. Okay? So this is a way to parse through a table of numerical values to express your function of several variables. Okay? Any questions? Now, a little bit more difficult to find out, but let's give it a shot to see if it'll work out for us. Based on this table, what if you look at your temperature and it says -3 degrees Fahrenheit, and then the wind was blowing, say you have a semi-accurate barometer. Is that what measures the wind speed? What measures the wind speed? Wind speedometer? Windsock? Those flags in the thing. I don't know if they measure speed, but they tell you which way it's going.
You see, it's like a fabric tree.
Yeah, it tells you the direction. It doesn't tell you how fast. You can kind of guess, maybe. So our table goes by increments of 5, and so if we have something a little bit more precise, like -3 degrees Fahrenheit for your temperature and 21 degrees or 21 miles per hour for the wind speed, you're going to have to do some interpolating here, right? Well, you could also plug those numbers in here, but who'd want to do that? So if you have a table, you can kind of make a guess. -3 degrees would fall somewhere over here, and 21 degrees would be over here somewhere. So you might be some spot over there. So what would you guess? I see a 22, 24, 29, 31. They're all negative. So can you throw a shot out there for a guess? -25. Somebody said -27. So those are fairly close. We're not going to, with the table, we're not going to get the exact value. I mean, you can find the exact value by putting it into the formula, but we'll not put it in the formula. Okay? All right, so this is our numerical representation for a function of two variables. We haven't formally defined it yet. I have the definition written down somewhere. VYI. Mathematically, this is our formal definition for a function of two variables. So a lot of times when a function is defined, they discuss the domain and the range. And so here they do the same thing. Function of two variables is a rule that assigns from a pair of real numbers, it assigns a unique real number. So that's what makes it a function. You know that vertical line test business, if it hits through more than one point, that means you have two numbers that you're putting in there, or two numbers that you're getting out from the one number you put in. That's how a vertical line test works. And so the same idea here. Wait, vertical line test now. This is going to be weird. Anyways, we'll talk about the vertical line test when we start looking at the graph of things. The domain is going to be what kind of numbers or what kind of things am I expecting from the domain on this function? Yeah? The set of numbers that passes through it. Okay, kind of close. Ordered pairs. So we're specifically for this one, we're talking about a function of two variables. So a set of ordered pairs, like x and y, would be an example of a domain. And then your output, your range, is going to be a set of just real numbers. So when you see this symbol over here, I know it has an x and it has a y and it has a function for its name, but really that whole thing is just a real number, scalar, if you want to think about it that way. And that's your output. So let's begin to imagine a graphical representation of this. Your domain are ordered pairs. Where does your domain live? If they're alive. What? No, not quite. XY plane. Okay, you got ordered pairs, XYs. So it must be on the XY plane. And we're calling it X and Y as your input, and your input is X, your input is Y. So let's call it the XY plane. So somewhere on the XY plane, all the real numbers that you're allowed to be able to put into this function, it's different for different functions, but any points that you can put into the function will live on the XY plane somewhere. And it might be the whole thing, but then it might not be the whole thing. And so when it's not the whole thing, people tend to just make some arbitrary blob, two-dimensional blob on the XY plane as your domain. But realistically, it doesn't look like that. It's either the whole thing, or it would normally be a quadrant or something like that, or some rectangular region. It might also be some circular region. And we'll take a look at some domains and ranges of things. But your output is just a real number. And right now I'm just going to say R for real number, but then your output, these points in here will eventually get sent to some set of values over here. Let's take some of those simple examples that we came up with. F of x, y equals x plus y. Now, what possible x and y value combinations can I put into this function? What? I didn't hear you. Anything. Do we say all real numbers? What's the input? Ordered pair. So, all real numbers squared? I know what you mean, but it's not all. We don't say all real numbers squared. So we say the whole xy plane would work. I think this is what you meant, William, right? But that doesn't mean real numbers are being squared. So all ordered pairs, the whole enchilada xy plane can be your input. And what's your output? Yeah, so imagine putting in some random numbers, x and y, random number for x, random number for y, and I can put any number I want, right? What do you think my possible range of outputs is going to be? It could be anything, and it could be all real numbers. This time it's a real number because our output is a real number. What if I have d, or what if I'm looking at x squared plus y squared this time? What possible numbers can I put in there? Numbers? What's all my possible input values? What's my domain? Not all real numbers. All ordered pairs, the whole xy plane. What's my range? Is it real numbers? Is it ordered pairs? My range. So real numbers? Am I in R2 or R? I'm just in R here for the range, right? Because the output is just one number. So is it all? Is it? What did you say? All positive? No. Including 0. So all positive numbers including 0. So you could express that in a couple of different ways. Yeah. I'm going to do this. Since we're getting all symbolic and stuff. I'll use the z variable. I can't use the x, I can't use the y because they're inputs, so I'll just use the z for my output. So z, bigger than or equal to 0 as long as z is a real number. All right, I'm immediately going to get tricky on you. Oh, that's not tricky enough. So, I have the square root of 1 minus x squared minus, this is a minus y squared. What do you think the domain's going to be?
X squared plus y squared is less than or equal to 1.
All right. You guys get that? Now, when we play this game back in pre-calculus where we have to find domains, we tend to look for square roots. Can't have a negative under a square root. We tend to look for fractions. Can't have 0 in the denominator. And then all the other restrictive functions like the logarithms. Logarithms have to be positive, right? So whatever's in the logarithm, you have to make sure that that's strictly bigger than 0. If you have those cosecants, those co-functions, they have a lot of vertical asymptotes, so you can't put in some of those values. So if you run into some of those weird functions where you have to find a domain, you just have to remember back in pre-calculus how you found the domain as if it was just a function of one variable. Here, when you're talking about a function of two variables, you'll still go through the same thought process. Say to yourself, I can have 0 under a square root, but I cannot have a negative. So I want this expression that's currently inside of my square root, I want that to express my domain. I want that to be strictly, not strictly, but bigger than or equal to 0. And if I get this, if I'm able to solve for one of the variables, great. If I'm not, like in this case, I'm not going to be able to solve for one of the variables, then I'm just going to have to try to express that and see what I can get. So if you were to solve for this, I would bring the -1 over to the other side, and then I would have to multiply or divide by a negative sign, which you know switches the inequality. So after those couple of steps, I'm going to have my domain to be all x and y values that satisfy this equation. So I can write that here as my ordered pair, x and y, such that x squared plus y squared is less than or equal to 1. Now that I have something a little bit more significant than just all real numbers, like in the previous two examples, now I have a figure, a two-dimensional figure that I can look at and say, hey, that's the domain. So maybe I can draw my domain. So including the circle itself is x squared plus y squared is equal to 0. And then everything inside of the circle. So this is my domain. Okay? The next one is range. What's my range? What are the possible outputs here? So you guys are saying 0. Let's establish that it can't be less than 0 because we have a square root, right? So I'm not going to have anything negative here. So it has to be bigger than 0. Now, why does it stop off at 1?
Effectively, any increase in the absolute value of that.
This? Okay, let's see.
So the minimum absolute value.
Like all those points, the radius will be 1. So at any point, you square them and add them. It's kind of like it's a circle. Like the radius will be 1 at any point.
Uh-huh.
Increasing x or y decreases the value. And we already know the lower limit. And decreasing x and y increases the value until you hit 0, at which point it becomes 1. And then any values for x and y, or any values for x squared plus, or any values for negative x and negative y have the same effect as their positive counterparts, so you can't be greater than 1.
Okay, I'll buy that. Sometimes it's just a matter of trying to plug in some values. You know your domain is a finite domain now, restricted. If you take a look at values that are on the circle, if x plus, on the circle, x squared plus y squared is equal to 1. If x squared plus y squared is equal to 1, that would make this 1 minus 1, which is 0. And if you go further in here, if you let x equal to 0 and y equal to 0, that's another possible point I can put in because that's part of the domain. If x is equal to 0 and y is equal to 0, I'm going to get a positive 1. And then it turns out that any other point that you try that's between the circle and the middle of the circle is going to give you a number that's between 0 and 1. So from the domain to the range, this is how we can try to express it graphically. Now, graphically expressing it like this is not as compact as we can make it. I have an xy plane and I have a z-axis, right? So what if we put the z-axis on the xy plane perpendicular to that, like we've been talking? We have been studying three-dimensional stuff anyways, right? So why don't we just view this in 3 dimensions? So that's what we're going to do. To visualize this graphically, we're going to view this. We're going to view the domain on the xy plane and then view the range on the z-axis, and then we can think about plotting points. Okay? So let's do that. So we've taken a look at the numerical point of view. We've taken a look at the symbolic, more or less a symbolic point of view. Now let's take a look at the graphical point of view. So generically, we have something on the xy plane, and then we put that, we take points from the xy plane, and then we map it on to some value on the z-axis. So instead of keeping them separate, now let's reimagine the output axis to be an axis that's perpendicular to the xy plane. And by reimagining that, we can combine this relationship by making points, and then we can combine all those points to make something. So let's take a look at the first one. So what we can do is we can be kind of primitive with this and make a table. I think a table like the Windchill Factor table can get a little too complicated, but let's say if we make a table like this, a little bit more like the table that we used to make in pre-calculus, then we might be able to combine these points a little bit easier. So we can pick some random points like 0, 0, 1, 0, 0, 1, 1, 1. And then we can figure out by putting the x and the y values in what these things are going to be. And then plotting them. Well, what are we going to plot? So these combinations in the table will actually give you a three-dimensional point with the x, the y, and the z. Now, I wouldn't necessarily suggest this when you're graphing these things, because when you're graphing these things, it might be better to get a more holistic idea, but we're going to approach this from really a piecewise point of view, like a dot-by-dot point of view. So if I were to plot these points, I would get 0, 0, 0. I would get 1, 0, 1. I would get 0, 1, 1. And I would get 1, 1, 2. So I get some points, but I'm not getting very far with this. Can you imagine what this thing might look like? Is it going to look like a solid block? Is it going to look like a surface? Is it curved in any way? It's probably going to be a plane. It's a plane. Right? And the thing to do is that if we had a nice computer program that would do this for us, we can just plug in points and try to piece those points together. But that's we would need a ton of points to get the nice visual. So let's see if we can approach this a slightly different way. Well, first of all, let me ask, you guys already said it's a plane. I said, yes, it's a plane. Are these things going to be solid or just surface? What do you guys think? So these things will be surfaces. Why won't they be solids? Z is one-dimensional, and that's your output. And remember, when you put an input, you're going to get a unique output, vertical line test. If it was solid, and you pass a vertical line through it, then you're hitting more points than just exactly one, or at most one. Okay, so it has to be a surface. All right, so let's establish that this is going to be a surface. And in this particular example, this surface happens to be a plane. And you know why? Because if you write f of xy as z, this is an equation of a plane that we already know. We know a lot about this plane already. We know the normal vector. We know that it passes through a specific point, or you can find a point that it passes through. But you know one special point where it passes through, right? Because it's 0 here, this thing must pass through the origin. And so you already know about this plane. All right, now let's do another approach. And this time we'll take a look at f of x, y equals x squared plus y squared. Now, we know something about this. We know something about this function already, because a couple of pages ago we said the domain is going to be all real numbers, and the range is going to be all positive z, including 0, but not negative, right? So if we start getting used to writing f of x, y as your z variable, that's like saying f of x is equal to sine x. Instead of saying f of x, we just say y is equal to sine x. It's kind of like the same thing. So z is equal to whatever that function is of two variables. So if we begin looking at it like this, and we've done something like what I'm going to say, we've done this before. If we know that it's going to be for certain values of z, why don't we let z equal to some constant? Now think about what this surface is when I let z equal to a number. When z is equal to 0, what is that? No, when z is equal to 0, it's the xy plane. When z is equal to 1, it's that plane parallel to the xy plane that's been lifted when z is equal to 1, right? When z is equal to some constants, this is just going to equal to a, not equal to, but this is going to be a plane parallel to the z is equal to 0 that's been shifted whatever k is equal to. Well, this is what it's going to be, yeah. But well, let's actually, yeah, you probably saw this and say that's a paraboloid already, which means you guys really studied your course. Ah, too bad that wasn't on a test, huh? Sorry. All right. Back to this business. When you let z equal to some constants, we'll try 0, 1, 2, 3 and see what happens. We're going to let x squared plus y squared equal to z. And let me just put like a whole bunch of them here. And then the idea is to look at that and say, hey, what kind of object is that? Individually trace, yeah. Like, what's this look like? This one kind of caught my eye. It's a unit circle, right? Circle radius 1. This is a circle of radius like square root of 2 or something. And this, what is that? It's just a point. We talked about this already. So these, if you put them not flat on the, well, we can see them flat on the xy plane. Let me do it flat on the xy plane. All together, but if you look at it from a three-dimensional point of view and put it on the appropriate levels, like this is the level z is equal to 1, and that would be up on a plane that's higher. This would be on the level z is equal to 2, and that would be up on a plane a little bit higher. And this would be at a level z is equal to 3, again up on a plane a little bit higher. And then try to imagine how this is going to look like. And Dave also mentioned, what did you say? Trace. Instead of letting z equal to numbers, why don't we let x equal to a number and y equal to a number? And we've done that before. Not going to do it right now, but you could trace them out as parabolas. And then you can get this whole picture of this. Whoa, what happened? There you go. Of this whole surface. So this here is a special name, though, for this set and this drawing. And this is one of the ways that we try to picture something in 3 dimensions if it's hard to picture. These are called level curves, or sometimes level sets. And we're going to talk a lot about level sets in the future. Okay? So this is the beginning of our new study of functions of several variables. The calculus on this is not going to be an easily transported calculus like we've seen with parametric equations. It's going to be a little bit trickier, but it'll be manageable. All right, see you guys on Monday.